Here we're being asked to find the expression for VA, the voltage across this 160 kilo ohm resistor. We're being asked to figure out what it is as a function of time, and we're not told what the interval is, so we're going to go ahead and find it at all times. For t less than 0, that is before the switch has been thrown. So the switch flips over at t0, so before t0, the switch is over here. That means there's nothing connected there, and we just have a one loop over on this side of the circuit. We have two resistors in series connected to this voltage source, so we can do a voltage divider to find the voltage across that 160 kilo ohm resistor. And so we find for t is less than 0, that VA is negative 60 volts, because notice the polarity of VA compared to the voltage source. They're opposite in polarity, so this voltage would be negative 60 from that perspective. If we want the voltage for t greater than 0, that's going to be after the switch is thrown, and in that case the voltage from the capacitor is going to be affecting VA. And so with the capacitor included in the circuit after t equals 0, we're going to have to find that capacitor voltage, and then we'll be able to find VA in terms of that capacitor voltage. So we're going to consider the capacitor, how it compares to VA. That means that we need to find the steady state of the capacitor before the switch is thrown when it's connected to this part of the circuit. So to find this voltage after t equals 0, we need to find the capacitor voltage. That means we need to find the voltage across the capacitor for t less than 0 as our starting point. So we're still looking for t is less than 0. The switch is still over here. We are assuming steady state. So we're assuming that the capacitor is acting like an open circuit. It'll have some voltage across that capacitor. We can see that V0 is in parallel with the 60 kilo ohm resistor, and so whatever the voltage is across that resistor is going to be our starting voltage for our capacitor. Since we have two resistors connected in series to a voltage source, we can use another voltage divider to find the voltage here, which will be the same as our capacitor voltage. So for t less than 0, we found the voltage VA. We also found the capacitor voltage V0, so that we can figure out what that capacitor voltage is going to be for t greater than 0. So now we'll flip the switch, and we'll find the new voltage across the capacitor, and then we'll use that to find VA. Here's the circuit that we have after the switch has been thrown. We have the capacitor voltage, which starts at 30 volts and will discharge, and we're trying to find that voltage so we can eventually find VA. So if we want to find the capacitor voltage, what we want to do is find the Thevenin equivalent circuit connected to that capacitor. And so finding the Thevenin equivalent circuit is going to be finding the open circuit voltage across the terminals where the capacitor is, and then finding the resistance connected to that capacitor. So the first thing we can do is to eliminate the capacitor, imagine it's not there, and find the open circuit voltage. Notice here this voltage is the same voltage that we have here. There's no path here, so there's no current through this resistor, so there's no voltage difference. So this voltage is the same as that voltage, and we can say that that voltage is going to be negative 60 volts, just as we saw for VA originally. Then the other piece of our Thevenin equivalent circuit is to look in at those terminals and see what the equivalent resistance is. We want to deactivate any sources. If we want to deactivate a voltage source, we want that voltage source to have 0 voltage, so we want it to be a short circuit. Looking in here, we can see that the 160 kilo ohms and the 40 kilo ohms are in parallel with one another, and that these two combined will be in series with the 8K. Thus, we were able to find the open circuit voltage, or the Thevenin equivalent voltage, for our capacitor. We were able to find the equivalent resistance connected to that capacitor. We know the initial voltage across the capacitor from before the switch was flipped, and so we can find the voltage across the capacitor as a function of time for t greater than 0. And so we found the Thevenin voltage, we found the equivalent resistance, we used the equivalent resistance to find the time constant, we used the equation to find the step response of this capacitor, and plugging in our values, we have an equation for the capacitor voltage as a function of time. The capacitor starts out charged to 30 volts, and as time goes on, that energy will discharge away, and at steady state, the voltage across the capacitor will be negative 60 volts. from that voltage source. But we're being asked for VA, the voltage across this resistor. So we know the voltage across the capacitor here, but we need to find the voltage across that resistor. So we need to go back to the original circuit that we have for t greater than 0, so we can compare the capacitor voltage to this voltage that we want to find. So we found the voltage across the capacitor here, but we want to know the voltage across that 160 kilo ohm resistor. And so if we're looking for a voltage, it makes sense for us to use nodal analysis. Since this is the bottom side of the known voltage and it's the bottom side of the voltage that we're trying to find, it makes sense for us to put our reference there. Then we know the voltage at this node here has to be negative 75 because of the polarity of that voltage source. The voltage here has to be VC, which we know, we have an equation for, and the voltage here is VA because that's how the voltage is defined relative to our reference. Let's say that we have currents flowing here and there. We'll call this I1, I2, and I3, and we'll be able to come up with an equation for VA. I'll multiply through by 160K to cancel out all of the denominators. We can do some algebra here, distribute the extra factors to each case, and remember that we know what VC is. We have an equation for that. We're trying to solve for VA, so we move all the VAs to the right side of the equation, and we can divide through by 25 to isolate VA by itself. But again, we know what VC is. It's a known function, so we can go ahead and plug that in and simplify to get a simpler function for VA. And so we're able to simplify this equation down to an expression for VA as a function of t. And so we're able to find VA as a function of t for t less than 0 and t greater than 0. There's a discontinuity at t equals 0. Notice how it jumps from negative 60 up to 12. The capacitor voltage has to be continuous, but the abrupt change in currents as the switch is thrown that are required to hold that capacitor voltage constant are going to give you discontinuities in the currents and in the voltages elsewhere in the circuit. Because we derived these two different expressions with two different assumptions, we have time intervals associated with each one of those expressions for VA.